Okay, so welcome back, everybody, and we continue second half of today. And our next speaker is Larry Goldberg, and Larry is a well-known practitioner and inventor of ZDM, the decision management, the decision model methodology. What he did together with Barbara von Halle, and now Larry is a chief evangelist of the product Sapiens decision that implements this technology, and plus DMN. But what is today very interesting, Larry is going to touch one of the difficult problem when we're trying to extract decisioning logic from the existing legacy applications. It's always difficult, and there were a lot of attempts, and probably many of us over years dealt with these problems. And based on Larry's presentation, it seems he has quite practical solutions. Larry, please take over.
Thank you, Jacob. I appreciate it. And I'm going to be sharing today some of our experience with what we call our automated logic extraction. That's our methods of extracting decision models from legacy code. And antecedents for this particular technology started many years ago, actually almost a decade ago, when Barbara and I tackled a very large project for General Motors to extract logic from their finance system, which was present in every dealer's showroom. I'm sure you've all had the experience of the sales guy in the showroom saying, excuse me, I have to go and pass this deal by our manager and get his approval. Well, what he does is he puts the deal into the General Motors finance system, and it spits out the responses that creates the contract and carries all the knowledge of that deal into General Motors. So we had just devised the concept of the decision model at this point, and it occurred to us that this would be an ideal solution for extracting business logic, and we evolved this idea, which has lain dormant for all these years while we were busy evangelizing and selling and creating the practice around the decision model. But last year, we began in earnest to develop technology to implement this idea. And what you see today is actually one of the very first projects that we conducted using this technology. And what you're seeing is that first, the first attempt at it. Since this project, we've evolved the technology quite dramatically. And I'll talk about some of that evolution as we go on through the presentation. So I want to talk very briefly about the transformation horseshoe. I'm sure many of you are knowledgeable of this transformation horseshoe. It was really invented over a decade ago by Carnegie Mellon, the Software Engineering Institute. And they devised this horseshoe. The notion of the horseshoe is that it's a three-sided shape. You have this notion of the architectural representation of the legacy or the base architecture on the left, the architectural representation of the desired architecture on the right. And as you go up the level of either side, you're going from the lowest level of code up to the highest level of architectural representation. You're going through these abstraction layers. And the notion across the top is the relationship of the base architecture and the base architectural representation at the base at every level, the source of every level, and its comparison or its relationship to the desired architecture. And the notion that was developed by the SEI is that it is possible to do a transformation of a legacy system at any level of the architecture. You could do from source code to source code a direct translation. You can do a code structure to code structure translation. You can do a function level to a functional level representation. And their notion was that the higher you go up in this horseshoe, the higher the value of the translation. And if you do a journey all the way around the horseshoe, so that you extract all of the source code, all of the architectural representation out of the base architecture, you decompose it and you reconstruct it from the architecture on down. In other words, you do a full trip around the horseshoe, you get the highest value of result, but it's the longest cycle. So here's the classic trade-off between time to do the project and the value you get from the project. And that's kind of represented by this diagram here, where we show what we believe to be the value add of extracting that atomic logic, putting it into, extracting the logic from within the legacy system, reconstructing it into decision models, and then implementing those decision models in terms of value add is a very significant improvement from most of the projects that are out there where logic fragments are derived from legacy systems and then reproduced in business rules and or in some form of code representation. And that was our idea back in the early 2000s, and that's what we've tried to implement in ALE, and it's been very successful. So I want to get into a little bit of theory of how we actually derive these decision models from legacy code, and we'll start with this notion of starting at the end. And there was some discussion this morning about building decision models from the bottom up. It's very unintuitive to me. It seems to be going backwards. When we evolved the decision model, it was our intuition that starting at the end, starting from the decision, was the most responsive solution from the business's perspective and from the perspective of producing a declarative structure. And actually, this spaghetti code is actually an IC diagram. And deriving logic from an IC diagram is most interesting and probably one of the greatest challenges in terms of actually extracting code. But our system or our approach worked exactly the same way for this IC diagram as it works for code. And the notion is to start at the end, to start with where we can see what amounts to a decision, and that is what we call an endpoint, a point at which the code actually puts out a result, delivers a result. And so the notion is, just as we do in decision modeling, is start with the decision, start with the end result, identify in the code the variable that represents that end result at the end, at the point at which it delivers that end result. Then trace that variable through the code to all the variables and the code that operates on those variables to result in the endpoint that you're looking for. And once you've identified those variables that influence the endpoint, you trace those back in exactly the same fashion, ultimately to the point at which you have input into the program. And what you've done is you've actually reconstructed the decision model that lies in the code, the machine model, as we call it. And then all that needs to be done is that we need to translate those variables into business-friendly terms, and we need to normalize the model so that it is a well-constructed decision model. And voila, we've done the job. And this particular project that we did for General Motors, we did not have the decision model technology. We just had, Visio and and Excel, but we were able to deliver these models to the folks coding the new system. It was a Pega system, and the implementers said that was the best requirements documents they'd ever received in any project. So that's really how we deal with the spaghetti, and that's the notion of the concept. So like any decision model, we start at the end, we identify that endpoint, we identify the variables, and we create the underlying rule families or decision tables in relation to each operation or each set of operations that's done on the consequential variables. And we keep going until done. And that way we create these decision models. Now, the magic is, of course, doing this automatically and doing it by code. And to do that, we've built a combination of machine learning tools and code to be able to do that, to crawl through the code, identify these variables, identify the operations, deconstruct the operations, map them into decision models, and then normalize the models that they can be input into a decision tool such as our own or any DMN tool. And so the idea of starting at the end, I'm sure everybody on this call is familiar with that, and that's the idea of actually building these relationships between the logic and normalizing them. It needs very little explanation. So the tool itself consists of three components. There's a preparation component, which goes in, crawls the code, creates a graph database of the code. And a lot of the time is spent in this archaeological process in determining scope. And that is deciding which part of this code is of interest, which are the outputs that we are interested in, and allowing ourselves to limit the scope to something manageable. We also, at this point, bifurcate the operation between the data elements and the logic elements. So the data elements is really identifying those variables that we discover and working at turning those variables into business-friendly terms. A lot of that work up to now has been done manually by consulting with analysts, but we are discovering techniques for automatically creating business-friendly expressions out of the variables. And a lot of that turns on how well the code is documented or how well it's commented. As Denny says, those guys who program tend not to write comments, but nonetheless, we are able to look at documentation. We're able to derive some business-friendly terms, but to date, most of our projects have been accompanied by a lot of work by people helping us map variables to business-friendly terms and mapping operators to operators that we recognize or that we standardize on. At the same time, there's a logic flow of work where we actually are doing this endpoint identification, tracing the flow, deconstructing and normalizing the logic. When we started out, we ended up creating massive structures of decision models because COBOL code in particular tends to be extremely complex in terms of multiple nested calls across multiple programs. But we have now managed to teach our tool to normalize that logic, simplify it, and create business-friendly interim fact types. And that way we're able to integrate directly into the decision. So I'm following a project that we did over a year ago, and things have evolved quite significantly since then, but they're evolving faster than we're building presentations. And in this project, what we've done is obfuscate the code so that you can't recognize the client's software, nor is the logic the same. But nonetheless, this is a real project with real code, and what we're looking at is the original archaeology. We're looking at some of the graph information that you derive from following the variables through the code. So we're going to follow the two traces of the operation: the data at the top layer, and the control flow tracking, and the auto conversion to decision in the bottom track. In the graphing of the structure, this is where our technology has moved very rapidly. This is an early control flow graph that we constructed. Today, our graphs are very, very rich, both with control flow and logic structures. And it's the means by which we're able to derive normalized models from the control flow. One of the really challenging aspects of this work is that there is a lot of data flow mixed with logic flow in legacy code, and we were having to unstring that and also develop methods to separate out the data constructs from the logic constructs in a meaningful way. And this led to multi-level graphs, or I'd say multi-layer graphs, and enabled us to achieve that goal, and also led us to interesting ways in which to represent data structures, or let's say the operations and data structures. In other words, visualize SQL calls. And that's an interesting area of modeling that we're pursuing right now to enrich some of this work. So here is a very simple explanation of how we're able to firstly trace the code from the endpoint you see on the right through an operation, in this case, simple evaluation of the data, to the input point on the left. So you see this trace of code, and you see the move on the left. You see an if-else statement in the middle, and you'll see a perform to actually output the data on the right. And that, and just before I show you the consequential model from this, I'll show you some of the work we did around the variable names to map them to business-friendly names. This particular project was done very manually. So you see the description as given to us in this column under the header description. This is how the business analyst described the logic, the variable, and you see the valid values on the right. What we did is reconstruct that into a business-friendly name using TDM methodology. At this point, it was done manually, but as I've said, we've evolved some fairly automated methods since then. And this is the point at which we are going to normalize that logic that you saw earlier. So we'll take you right into it. So this is a flow, this is a decision flow of decisions that represent the underlying code. And within this subflow here, there are two decisions that we identified, and we're going to actually drill into this particular decision that represented that little piece of code that I showed you a little earlier, or at least at which that little snippet of code I showed you earlier actually resides. So this is the decision itself. And you'll see that the decision is broken into sub-decisions, what we would call rule families in TDM. The interim decision was created by the tool. These variables, these interim fact types was created by the tool and named by the tool. And here is one of the decisions taken from that code. You'll see how we've translated some of the interim fact types and how we translated it into a standard decision table. And one of the real value statements of doing what we do is that we're able to, in our tool, test the logic that we derive directly. So once the tool has created the decision model, we're able to test input and output, build test cases, or import test cases that were created for the underlying COBOL code and actually test them to see if we get the exact result expected. This is a typical test case running in Sapiens Decision, showing the result from the code, showing the interim results from the code, showing the inputs, and we're able to, and this is a true value add for our clients, is they're able to test the COBOL code directly against the decision models and ensure that the results of the one is exactly the same as the other. And we're getting very accurate results from this method. And here is the test running across the decision. You'll see the results internally in the decision. It's a great method of how to trace problems in the logic, and how to compare and how to determine whether or not the logic is following the path expected. And we're able to look at the results in the decision tables themselves as well. So that really is all I've got to show you guys, but I'd be very happy to answer any questions about the method and the product.
I don't see anything from the audience members, but I think Jacob, you had some comments or questions. Do you want to just unmute yourself and go ahead?
Yes, actually, I also have experience to migrating COBOL-based applications to rules-based systems, and even before rules-based was just migrating from COBOL to C++, and it's always a challenge because it's two different way of thinking. COBOL is completely, they have even not go to, but go to this line, right? And performs that's something that violates all logic when nobody follows this logic.
Right.
And my first question is, how did you actually replace this piece? That was one of the strange, they're completely different paradigms.
Yeah, so the way we do it is that we assign a variable name to that line, and that's one method. Actually, it depends on the nature of that. It depends on the context of that particular go-to. But one method is to assign a name, a variable name to that line, and then create an object of that line. So, but you know, the challenge is every new piece of code has its own new challenge, because every new piece of COBOL has a new challenge, because as many COBOL programmers there are out there, there are that many methods of implementing COBOL code. And so the good thing is that when you get a large system, classically, the methods across the system tend to be the same, although they're different from all other methods in all other systems. So you learn, and the machine learns. And so ultimately, that's the approach. But what is very successful is this method of being able to represent this very, very procedural code in a declarative form. It simplifies dramatically. We see a collapse from thousands of lines of code to, you know, one fairly compressed model and this makes maintenance, and it makes management of the system, it makes conversion of the system very good. One of the problems of converting code to code is that really all you're doing is you recreating legacy code. You're simply creating code which is going to be unmanageable within a few years again. And so when you create the decision model, you have a highly manageable asset and a valuable business asset to take forward. And one question I see on the board is that did we discover a lot of mistakes or errors in the original classic code? I wouldn't call them errors. I would call them issues that the business was unaware of in the code, or factors in the code that the business was unaware of. Most of this code is very, very long-standing, and so most errors would have been discovered, I think. But what is interesting is that how the business discovered from the code that from the models they saw how convoluted the logic really was, and how much simpler they could make the logic, how much more responsive to the business requirements could they have made the logic. So, and then there's another question about redundant COBOL code. Yes, I mean, our second project, about half the code we looked at, or half the code we recovered, the business said, no, that's not of any interest. We no longer use that. So we were discovering huge amounts of redundant code. But there are tools for discovering redundant code, and those tools are actually quite useful, and we use them actually in our methods because we reduce the amount of work we have to do. But yeah, you discover some very surprising things when you do this the first time. One of the real facts are that there's a whole community. Every one of these large legacy systems have a huge community around them, and this community have tribal knowledge. And so when you extract these models, you get a lot of activity from the tribe saying, "Oh, I didn't know that was there. Oh, I remember this from 20 years ago," and so on. So yeah. Mark says he calls it accidental complexity, when people make rules more complicated than they need be. That's absolutely true. That's absolutely true. This particular example here was an example of that. Huge complexity to do something which was actually quite simple.
It's interesting, Larry. I find the same thing with processes. I work more on the process side, but it's the same thing. There's this sort of institutionalized ideas of how complicated something is, and they get caught up in like, well, we've always done it that way, but it doesn't have to always be that way.
Yeah, you're right. I mean, one of the values of decision modeling and one of the decision model approach is the ability to remove that complexity out of process. So just as a declarative model creates simpler code for complex procedural code. So if you start extracting what can be, declarative factors out of procedural processes, you can simplify those processes very, very nicely. So Jan says, why accidental? I would call it intended complexity.
Yes, I saw that. I like. And then Mark says he's giving them the benefit of the doubt. So
I think, yeah, Jan is right there. It is intended complexity.
So we have a question there from Alan as well. With legacy code, often the things you think of as decisions are represented in the output as a set of interrelated flags and variables.
Yes.
Do you also refactor the outputs, or do you stick to these as the starting point?
No, absolutely we do. We turn them into business-friendly terms. And that's where the machine really needs support. Right now, the machine is very good, has become very good at normalizing these complex structures and actually removing some of the complexity itself. But recognizing where that output is a technical term and needs to be simplified into business-friendly terms, that's still somewhat human. I mean, what is exciting is that our multi-level graph now is opening the door for us to actually take natural language documents and extract the language, the logic out of them in much the same way. So that's become, you know, I think the most exciting direction for us in this tool, and where we think we're going with this tool in the future. So we have quite a few projects now with rules, business rules, large-scale legacy business rules projects where those rules have become, you know, just like legacy code, very, very, very complex and very, very procedural. We are extracting the logic from them, turning them into models, normalizing those models, simplifying them dramatically. I mean, the collapse in terms of size and complexity is very dramatic.
Well, and I think that that's, we're sort of seeing in the comments or the questions from Carol Ann and Lloyd, is that Carol Ann is saying in a lot of COBOL systems that they had to modernize, a portion of the logic was added before and after the COBOL program because nobody wants to touch that code. And then Lloyd is also talking about incremental replacement of the legacy code. And is this, you know, intended to be integrated, or is it really about ripping that out and replacing it?
In one of the largest ever projects we did, it was a core banking system, a gigantic core banking system, one of the largest banks in the world. We did this incrementally. We literally tackled, firstly, of course, we did it, they divided this project into components. Then within the components, we tackled certain aspects first, and we did it absolutely incrementally, subsuming some of the externalities at the same time as we were doing the model. So it's very, very difficult. And Don Perkins said, I've had clients who are defensive for the complexity, and it's very difficult. The culture is more difficult than the actual technology, because people become, you know, they become comfortable with their complexity. They understand this complexity. They live with that complexity. And you see this in, you know, a lot of these procedural processes that you were talking about earlier. For them, you know, when you do define it down to its simplistic declarative terms or its simplistic, you know, clarity, it's somewhat uncomfortable for them. So, yeah.
No, that's good. Well, thank you very much, Larry. We're running a little short on time now, but definitely there's some other conversations going on the Slack channel if you want to check that and maybe respond to some of the things there. So
thanks very much.
We're going to get ready for the next presentation.